This is the second in a 2-video series from Chapter 8 from Engineering Economic Analysis by Donald Noonan et al. In this video, we're going to pick up starting with example 8-4, which is looking at a graphical solution for choosing between 3 different materials for a pressure vessel. This pressure vessel is expected to last for 50 to 75 years, will not have any salvage value at the end, and the less expensive option is expected to last not nearly as long as the more expensive option. And so in this case, we're going to do an annual evaluation. We're going to look at this in terms of an expected uniform annual cost, because there won't be any direct benefit other than this is going to serve the purpose that we have, and all of them will have the same benefits for the year. But we also want to look at them uniformly based upon the fact that they have different useful lives. And so since brass has a 4-year useful life, stainless steel has a 10-year useful life, titanium has a 25-year useful life, going back to a present worth analysis would not be a fair comparison, because you would have to think about, well, every 4 years we're going to have to replace the brass one, every 10 years we're going to have to replace the stainless one. Just doing it as a uniform basis allows us just to go about computing the annualized cost and then just compare that directly, realizing that the built-in repurchase every useful life is already in the annualized cost estimate. And so what we see here is if we sweep the percentages, all we're doing is just going and projecting $100,000 over 4 years at various interest rates for brass. And brass, as you can see, is the solid black line here. And so this is the EUAC for brass. And then we did the same thing for stainless. This is projecting $175,000 over 10 years. And so if you look at different interest rates, that's this dashed line coming across here. And then titanium is the dashed blue line, and so that is $300,000 projected over 25 years. And what we want is the one that has the lowest EUAC. We want to minimize our cost. And it really depends upon what our interest rate is as to which one is the better deal. And so the best choice is actually highlighted in blue. And so for titanium, it works out that at low interest rates, titanium is the better choice. At moderate interest rates, the medium range of interest rates from about 6.3 to 15.3, stainless is the better choice. And at high interest rates, the lowest cost, the brass pressure vessel is the better choice. And this graphical solution allows us to simply look at the plots, figure out where there are some intersections, and where one value becomes a better deal than the other. And so we have marked titanium in this region is the best choice, stainless in this region is the best choice, and brass in this region is the best choice. We can also look at this in Excel. So if we go here, what this spreadsheet is attempting to do is use goal seek to determine the intersection. So if we look at the previous slide, we saw that there was an intersection somewhere right around 6, and you see we determined at 6.3, and then there was this intersection between stainless and brass somewhere a little beyond 15, and we determined that was 15.3. It's a challenge unless you've really plotted in high resolution to figure out exactly where that intersection is. And so what we can do is we can actually use Excel for that. And so in Excel, what we're going to do is put in our useful life, N. We're putting in our present value as a negative number. There's no future value. We're not going to get any salvage value out of this. And then we're going to use the PMT tool in order to figure out at what interest rate we see the difference between the EUAWs go to 0. And we're going to use goal seek. So I'm going to switch over to Excel and show you how you can do that. So in Excel, I have prepared 2 Excel spreadsheets. These will be posted onto Blackboard alongside the video, but what you see is I have set up brass, stainless steel, and titanium, and then their useful life is in here. And so at 6.28%, what you see is that stainless steel and titanium have the same EUAC. And the question is, okay, how did we determine that? Well, what we did was I set this as the free moving variable, and I wanted to put all of these calculations at the same percentage rate. And so this is where I is independent to move, and then down here this simply equals B2, so that's going to be the same interest rate as we're using for brass. This is going to be the same interest rate also, and then down here, just to showcase, these are all at the same interest rate. And so what we're going to do is look at the difference between stainless and brass, and what we want to do is just allow the EUAC to be calculated freely. And so these are just calculated based on whatever interest rate gets set over here. EUAC is calculated using the payment calculation. And so that's based on the interest rate. That's coming from our I over there in column B. And then based on the number of periods, that's the useful life. That's coming from column C. And then we have the present value. That is the cost of that particular vessel. We're not putting in a future value because that just goes to 0. It's explicitly listed in column F, but there's no reason to put it in the PMT function because it defaults to 0. And so if we wanted to figure out at what interest rate is the EUAC of brass and stainless steel equal, what I have down here is D3 minus D2. So that's just looking at the difference between the EUAC of stainless steel and brass. And so if I go up to the data tab, I do a what if analysis and I choose goal seek. What I want to do is figure out where do the EUAC values intersect. And so I'm going to set cell D6, which is the difference between my stainless and my brass, and I want that difference to go to 0. And what I'm going to change is my interest rate. So I'm going to pick this cell here, which is ultimately going to change all of the interest. And so if we say OK, it'll go through a goal seek and it will manipulate the I value until those are equivalent. And so what we see is at 15.25%, the EUAC of brass and of stainless steel are equal. So that is the intersection point that we see at 15.25%. And then we can do the same thing with another goal seek down here to get our titanium and stainless intersection point. So we'll go ahead and do another what if analysis, do a goal seek. We want that cell, now D7, to go to 0 by changing, again, the same interest rate. Okay, so we have that, and now we see that happens at 6.28%. And so if we go back into our PowerPoint here, this is how we were able to determine that we have an intersection at 6.3 and 15.3. And if we look back at our graph right here, this is the 6.3, that's the stainless and titanium intersection, and the 15.3, 15.25, that is the intersection of the stainless and the brass. Going on to example 8-5, we have another graphical solution. Here we're choosing between 3 different machine alternatives. They each have different initial costs, and they each have different uniform annual benefits and different useful lives. So we're going to do a very similar analysis here, but now one thing we need to be conscious of is it may perhaps not be a good choice to pick any of these 3. And so in this case, if you go about doing the same kind of analysis, figuring out the EUAC, in fact EUAW actually, we're going to compare this as a total worth because we have the cost and then we also have some benefits. So we're doing an EUAW analysis in this case. And so that is going to be looking at this as a benefit and then subtracting off the annualized cost based upon the initial cost there at different interest rates. And what we will see is at low interest rates, machine Y is actually a better choice. At modest interest rates, machine Z is actually a better choice. Then we get to machine X, but what you notice up here is after a significantly high interest rate, somewhere beyond about 22, 23, 24%, somewhere up there, all of the choices, X, Y, and Z, end up having a negative EUAW. And what that means is it would be better for us to do nothing at all than to do any of those alternatives. And so what we can do is actually look at, again, an incremental change, looking at X relative to Y, X relative to Z, Y relative to Z, and also compare those to the do nothing alternative to see which one is best. So we can figure out here, where is that Y-Z intersection? And so yet again, we can go back into Excel. And so let's go back to our workbook here, and we're going to change over to our example 8-15. And so right here we see Y has the best EUAW at low interest rates, followed by Z coming up at middle interest rates, and then here we have X until we get to a point where all of them are negative, in which case doing nothing is the better choice. So let's go ahead and look at our calculation here. In this case, our EUAW is equal to B3, so that is our uniform annual benefit, minus the PMT that we get at the interest rate, in this case 1%, time, and then we also give it the number of periods, so that's the useful life, in this case 6, and then we're putting in negative the initial cost, so negative $2,000 in this case. And so we're recalculating all of this for X, then we're doing the same thing over here for Y, and we're doing the same thing for Z. If we want to figure out the intersection, so right now I have this computing in 1% intervals, but rarely is the intersection exactly at an integer percent. What I can do is I can look at the difference between Y and Z. So I'll go ahead and say Y minus Z here, and I'm going to look right here. This is the closest that I see them, and I'm going to do Y minus Z, and I can yet again do goal seek. So do a what if analysis, do goal seek, and I want that cell to go to 0. I want the difference to go to 0. I want to know where that intersection point is, and what I'm going to change is going to be this interest rate right here. And so what that tells me after analysis, it still looks like it's 3%. If you actually click on it, you can see that it's got a lot more decimal places than that. And so if you go back to the home layout on the ribbon and you move the decimal places over, you can see that about 3.134% is where Y and Z have the same EUAW. We can do the same thing down here, trying to figure out, okay, at what point is X the better choice? And so we could make another column here and say, all right, this is going to be our X minus Z. And so we'll put this down here and say equals X minus Z. And we want that to go to 0. So we will go back up to our data and we will do what if analysis, goal seek. We want that cell to go to 0 by changing the interest rate over here. Okay. And we see that this comes out to 10.8031%. And we can actually see that displayed by moving that over. And so, using goal seek allows us to showcase the percentage at which we have the same EUAW. And so that shows us the difference between Y and Z. That allowed us to figure out what percentage that intersection happened. And then up here, we figure out at what percentage this happened. If we want to figure out when does X go to 0, we can go back into our book
and just figure out, okay, it's looking like it's getting close to 0 here. Let's figure out at exactly what percentage this goes to 0. So we'll again go to data, do a what if analysis, goal seek. We want that cell to go to 0 by changing the percentage here, and that happens at 16.68%. And so if you look at the graph here, we see that was X going to, let's see if that's what we had here. Oh, sorry, that was Z going to 0. Let's go ahead and see if we can get X to go to 0. So X is getting close to 0 down here. And so let's do yet again another goal seek. And so we want B30 to go to 0, and we're going to change our interest rate right here. And so we see that X goes to 0 at 23.21%. And so here, this do nothing intersection right here is at 23.2%. And so you can do a 5-button analysis. That's what we very similarly set up. You can do some goal seek, looking at differences there, just like we did before. Incremental analysis is another important consideration, and so this can be done with internal rate of return. We can do present worth. We can look at our expected uniform annual cost or annual worth. And so what we're going to do is look at what is the incremental difference between a lower cost alternative and a higher cost alternative. So obviously the higher cost alternative is going to cost us a little bit more, but in terms of the benefits that we receive balanced out with those costs, is the higher cost alternative a better deal? And so this is what's known as a challenger-defender analysis. And so the defender is at that point the best yet identified alternative. So we'll start out generally with the lowest cost alternative and compare that against the do nothing choice. And then if that turns out to be better than doing nothing, we'll move on to the next least expensive alternative until we've gone through all of the comparisons. And so for n mutually exclusive alternatives, we'll need n minus 1 challenger-defender comparisons. And this just allows us to compare to next up, next up, next up. We could, of course, have a lot more comparisons, but this makes a nice standard way to just go progressively more expensive as we go through. So in this case, in example 8-7, we have some pairwise choices between 5 different alternatives. And so you can see in the top table we have the initial cost and the uniform annual benefit. So A costs $4,000, gets us a uniform annual benefit of $639. B costs $2,000, uniform annual benefit of $410. C costs $6,000, uniform annual benefit $761. D costs $1,000, uniform annual benefit of $117. And finally, E has a cost of $9,000 and a uniform annual benefit of $785. And what we're doing in step 1 is just rearranging those in order based upon their initial cost. So D is the lowest cost alternative. That's where we're going to start, and we're going to work our way pairwise until we're comparing to E. And so the first thing we're going to do is calculate the internal rate of return for D. In this case, you would generally do it for the least expensive, and we're going to see if it's better than doing nothing. And in this case, we're going to use MARR. So if we don't have an interest rate that's at least 10% in this case, that is our minimum attractive rate of return, then we may as well do nothing. We're going to say that it's not an attractive alternative unless we can get at least 10%. And so in this case, if we do a present worth analysis of D, and we want that to go to 0, so we're going to say negative the initial cost, negative $1,000, plus the uniform annual benefit,
and then we'll have to figure out this PA IRRD for a 20-year useful life. All of these will have a 20-year useful life with no salvage value at the end. And so if you solve for this, what you'll do is put 1,000 over to the left-hand side, add that to both sides, divide by 117, and then figure out what PA value for 20, what interest rate will you get a PA value for 20 periods, gives you 1,000 over 117. And you can do that using some interpolation, or you can just directly solve for the interest rate given the formula for P given A. As it turns out, the IRR in this case is 9.94%, very close to 10, but still not at that 10% threshold. So in this case, we're going to say do nothing is still the defender. That is the best alternative that we have between doing nothing and choosing alternative D. And so now we're going to move up the scale, and we're going to calculate the differential IRR of option B compared to do nothing. Do nothing right now is the defender, and B becomes the next challenger up. And so in this case, our present worth of B is going to be negative $2,000 plus 410 times P given A at the prevailing interest rate for 20 periods. And if you solve for your IRR in this case, you get that it is 19.96%, certainly well more than 10%, meaning B is a good choice and better than doing nothing. We already discounted D and said D is not a good choice, so B is better than doing nothing and certainly better than D. And so now we will compare that to A, and so in this case we are going to look at the delta IRR. In this case, we didn't, even though this was a delta IRR, we didn't have to subtract anything because the cost of doing nothing is 0 and we get no benefit from that. So in this case, there's an implicit minus 0. Now what we're looking at is A relative to B, and so in this case, we have a cost looking at the difference between the cost there. So 4,000 minus 2,000 compares A and B. And then we're going to look at the differential benefit. In this case, we get 639, which is more than the 410 that we expected before. So we have a $229 net difference in benefit for a $2,000 net difference in cost. And if we go about solving for IRR here, that is less than 10%. And so now we move on and we say, well, A was not a better choice than B. So B remains the defender and the challenger is defeated. So now we're going to compare B to C. And so in step 5, here we're calculating the delta IRR for C relative to B. So again, C costs more than B. We're going to take the more expensive minus the least expensive, so we get 6,000 minus 2,000. Here's the difference in benefit, and we need P given A at IRR. Once we solve this out, we see that IRR comes out to be 6.08%. That is less than 10, so B remains as the defender. Now we do our final comparison, B to E, and we notice that E cost $9,000, so we get 9,000 minus 2,000, so a $7,000 differential in cost, and $785 in benefit compared to $410, so we see $375 in difference. And when we solve for that, our IRR is minuscule, 0.67%. That's less than 10. So that means alternative B remains the defender. There are no other challengers to consider. So alternative B is the best choice based upon a differential analysis, an incremental analysis. In this case, incrementally looking at one relative to the other. In this case, this is what we determined using 10% as an MARR. One of your homework problems has a different MARR, but you can go through a very similar analysis procedure following through with that. So, to summarize Chapter 8, with the alternative analysis methods that we have talked about thus far, if we know our MARR, we know our minimum attractive rate of return, we want to know, are we getting an IRR that is at least equal to our MARR?
And we can do that through a present worth analysis or an equivalent annual. And if we don't know what the MARR is, what we can do is this graphical approach, just looking at one option relative to another, and say, well, if we don't know what the interest rate is, the MARR we're going for, we can just say, well, if it happens to be low, then this alternative is better. If it happens to be in the middle, this alternative is better. And at some point, all of the alternatives may, in fact, go to a negative present worth or annual worth, in which case doing nothing would be preferable. And we can use spreadsheets that allow us to figure out those intersections. We can use GoalSeek to figure those things out. And if a graphical approach shows that you have close equivalent values, you can pick one or the other. So right around the intersection, there's really not a major benefit of one versus the other. Rate of return analysis is often easier to explain. This gets you a better return on your investment, is typically how a lot of businesses would look at it. So if I spend this amount of money to get you this equipment, what kind of return would that have for the company? A lot of firms also have a preferred measure, and if you use their measurement, use that, whatever it is that your company decides they want to do for alternative analysis comparison. So this ends our Chapter 8 coverage.